Good morning, guys. Today we'll talk about exponential and logarithmic models. The very first one that we'll talk about is a growth or decay model. Now, in physics and in a lot of certain applications like wildlife populations, if you want to figure out how many rabbits, for example, there's a story about I think an Australian guy who released 10 rabbits. I can look up the video on YouTube and attach it to the classroom. Who released 10 rabbits into the wild forest because he wanted to have some rabbits to keep. And before he knew it, the rabbit population had grown to over 10,000 rabbits in a very short space of time. So situations like that can be modeled using exponential growth or decay models, and financial investments can be modeled or using this kind of model as well. But the most common application for this in science is in exponential growth or decay of organisms, which is called carbon dating. Trying to figure out how long ago did this animal die. If I find its bone X amount of years. People that discover fossils, I know you've heard about people that discover fossils, use carbon dating to figure out how long ago did these animals live or die. They do that by comparing the ratio of the isotopes in carbon-14 to the isotopes in carbon-12, which is found in the air. The isotopes in carbon, I think 14, start decaying when the object dies because it's no longer being replenished by either the body or the plant itself. It's no longer being replenished. Anyways, enough chemistry. And the idea here is just that we're using a mathematical model to be able to get or predict certain things like time, like age. So in this model, N0 is the initial value. If you're talking about radioactive decay, then it's the initial mass of the substance. If it's an investment, then it's the initial investment. If it's a wildlife population, maybe 10 rabbits, then your A0 is the initial number of rabbits. T is the time that it takes for the quantity to double, or the time that you're interested in. K is the growth or decay factor. If K is positive, then you have exponential growth, and if K is negative, then you have exponential decay. Let's look at some examples. If a population of bacteria doubles every hour and the culture started with 10 bacteria, express the population of the bacteria as a function of time. So we know that y is equal to A0 e to the power kt, right? When you look at this question, we've been given some information. It's doubling every hour, so that means that after 1 hour, which is the time, we'll have twice the initial amount, right? Because it's doubling every hour. And then we have some more information here. If the culture started with 10 bacteria, so that tells us that the initial amount is 10. Express the population of the bacteria as a function of time. So they just want us to write the equation for this model or for this situation. So I need to find out the value of k, and I need to find out, I just need to find the value of k, then write the equation. So initially I know that when time is 1, the y value or the thing has doubled. So I have twice of A0, which is 20, because A0 is 10. Twice of A0 is equal to A0, which is 10, times e to the power k times, and this happens when the time is 1 hour. So 1 hour. So I have 20 is equal to, not 20. If I divide both sides by 10, divide by 10, then I have 2 equals e to the power k. And if I introduce natural logarithm on both sides, I have natural logarithm of 2 equals is equal to x, right? Is equal to x, because natural log e is just 1. So I know that that's k. That is k. That is k, not x. So I know that my k value is natural log of 2. So in this equation, instead of having a k value, I'll just have y equals a naught, which is 10, times e to the power natural log of 2 times t, right? E to the power natural log of 2 times t. Now if I try to do some more simplification here, just stick with me for a bit. E to the power natural log of 2 times t is the same thing as e to the power natural log 2, right, to the power t, because the powers would still multiply. Let me write that more clearly so that you can see it. What I needed is this part right here. This is enough for my equation, but just let's see if I try to work this further and see where it takes me. This is natural log 2 to the power of t, right? Because if there is a power on the power, then the powers will just multiply. Because if I multiply the powers, I go back up there. Now I know that e to the natural log is an inverse function. So e of natural log of 2 is just going to be equal to 2, right? And there's a power of t outside that, so I just have 10 times 2 to the power t. Now if you remember the very first time we talked about exponential growth and decay situations, we said that y is equal to the initial value, which you can call a naught, times the growth or decay factor to the power of x, right? And I hope you can see that since this is doubling, the growth factor is expected to be 2. The x is the time, and the a naught is the t. So I can think of this in two different scenarios, and this will be convenient if you have a specific rate of growth, for example, doubles or triples or something. Then it will work out nicely like that you can just use this formula that the y will be equal to the initial value, which is a naught, times the growth rate. If it's given, if it's tripling, then it's 3. If it's doubling, then it is 2 to the power of x. So since I've been given the initial value, then I'll just have 10 times 2 to the power t. What I'm trying to say is that we could have gone straight here after knowing all of that information without having to go through this. But like I said, it's easier, it's more convenient if this growth factor has been given as a clear-cut rate like double, triple, quadruple, etc. Okay, so this is the alternative that I was talking about. You could just say y is equal to a times b to the power x. A is the initial value, b is the growth rate, and x is the time. So this would be your equation straight away. And this nicely shows us that this model, right? This model is consistent with even already existing knowledge about exponential growth functions. This model is consistent with all kinds of exponential growth relations. Okay, how many hours will it take for the population to reach 200? So they're asking us for the value of t when y is 200. T when y is 200. So I'm just going to substitute for y as 200 equals 10 times e to the power t natural log 2 or natural log 2 times t. Because remember, I had got this equation, natural log 2 times t already. So that's the equation I can use. Or alternatively, you can use this other equation. You should get the same answer. So if I'm using the equation from the model, and again I'll try to write very clearly. If I try to use the equation from the model, then I'll have 10 times e to the power t, t natural log 2, which is the same thing as natural log 2 times t. Divide by 10 both sides, divide by 10, divide by 10, I have 20 equals e to the power t natural log 2. If I want to get rid of the very distinct things, if I want to get rid of the e, I'll introduce natural log both sides. So natural log 20 is equal to natural log e to the power t natural log 2. Simplify that, and I have natural log 20 is equal to natural log e cancels out, so I'll just have t times natural log 2, divide both sides by natural log 2, natural log 2. So t is equal to natural log 20 divided by natural log 2. So that is how long it will take for this population of bacteria to reach 200. If I do that on my calculator, it's natural log 20 divided by natural log 2, 4.32 hours. 4.32 hours. If I use this other idea, the basic idea of exponential growth, my initial value is 10, this is 2. I'm looking for the time value when this has grown to 200. So again, I'll divide by 10, divide by 10, and then I end up with 20 is equal to 2 to the power t. The only way I can bring this power down is if I introduce a common logarithm, and I can introduce the natural logarithm on both sides, natural log 2 to the power t. The power will come down, so I'll have natural log 20 equals, this power drops down to the front, t natural log 2, and it's the same thing as what I had earlier, because if I divide both sides by natural log 2, then this is natural log 20 divided by natural log 2 equals t, which is the same answer, 4.32 hours. So yeah, that's that model. Another equation, another question about this, another example is carbon dating, like I told you earlier. If the half-life of carbon-14 is 5730 years, this means that it takes carbon-14 5,730 years to decompose to half its original mass. If its original mass was 2 kilograms, then after 5,730 years, its new mass will be 1 kilogram. That's what half-life means. Express the amount of carbon-14 remaining as a function of time. Now, this one is as a function of time. I'm going to use my initial model. Y is equal to n naught e to the power k times t, right? To the power k times t. So I've been told that its half-life is 5730 years. What that means is that after 5730 years, when the t is 5730, right, the new amount left will be half of the original amount, right? I hope that makes sense. Because half-life is the time it takes for something to decompose to half its original mass. So that means I mean to half its original mass or composition. So that simply means that after that time of a half-life, I'm just going to write this again. After that time of a half-life, after 5730 years, the new amount, which is the y value, because this is the x value, the new amount is half of the initial amount. If the initial amount is n naught, the new amount is half of n naught. So this information is going to help me to find the k value. It's going to help me find the k value. So substituting that information, I know that y is now a naught divided by 2 is equal to a naught times e to the power k times the time for that to happen is 5730 years. So the a naught cancels out. Hope you can see that, because I have a naught both sides. Half is equal to e to the power 5730 kt. No, sorry, 5730 k, not t, because the t is 5730. This is 0.5 equals e to the power 5730 k. Introduce natural log both sides. Natural log 0.5 equals natural log e 5730 k. So I have natural log 0.5 is equal to natural log e cancels out, so I have 5730 times k. That means my k value, my growth factor, or my decay factor, since this is a decay expression, my decay factor is going to be natural log 0.5 divided by 5730. Now I can use my calculator to check whether or not this decay factor is positive, or negative. If it's positive, that will mean its growth, which will be inconsistent with this situation because this is a decay situation. So I expect my k value to be negative. So if you try this on your calculator yourselves, you do natural log 0.5 divided by 5730, you'll come out with negative 0.000121, round up. So this negative proves to me that my work is consistent because I expect a negative growth factor from this situation because it's a decay situation. So since I have my k value up here, I can express the amount of carbon-14 remaining as a function of time. So my equation is going to be y is equal to a naught e to the power k, which is this whole thing. I don't want to write that, so I'm going to write this. Natural log 0.5 divided by 5730 times t, right? This is my expression for the carbon-14 remaining as a function of time, okay? If you want, you can write this whole negative thing there. But that's a naught e negative 0.123121 times t. That's your equation. Okay. So the alternative, if the half-life of carbon-14 is those many years, the alternative, am I able to think about this in the way that I thought about this? I mean that I thought about the other example earlier. Am I able to think about it that same way? Let's see. Because in that same way, it was y is equal to a, which is the initial value times the growth factor to the power t, right? So am I able to think about it like that? The initial value is a naught. The new value is going to be a naught over 2. This is the new value, which is a naught over 2. The growth factor, since it is half-life, right? The decay factor is going to be a half to the power t. That's going to be my decay factor. But I know that my t is 5730. So let me take out the half. I know it's a half, but let me take it out so that I can calculate for my k value. I can calculate for the decay factor. So a naught cancels out, and then I'm left with 0.5 on this side because it's 1 over 2 is equal to k to the power t, which is 5730. If I introduce natural log both sides, natural log 0.5 is equal to 5730 natural log k. What is happening? Wait. Yeah, we could. So I should have been calling this b, not k. So this is b because it's a growth factor, right? B is the growth factor, so let me just keep that as b. And if I try to solve for b, then I'll have natural log 0.5 divided by 5730 divided by 5730. So I'll end up with natural log of b is equal to natural log 0.5 divided by 5730. If I want to solve for b alone, my growth factor, I'm going to introduce the exponent to both sides. E to the power natural log of b will just give me b is equal to e to the power natural log 0.5 divided by 5730. Now, this equation, I can now write it as y equals a naught times e, because the b, which is the growth factor which I just solved for, is e to the power natural log 0.5 over 5730, right? And I hope you can see that this equation is the same exact equation as what I had previously. This this one right here. So those are two alternative ways to figure this out, and you can use whichever one is more convenient for you. The half-life of carbon-14, blah blah blah, expressed out part A. Part B. Bond fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bond? Right? To the nearest year, how old is the bond? I have two equations. I can use this equation, which is a naught e to the power this, or I can use this alternative equation, which is a simplification of this equation that I have here. How does it simplify to that? I'll show you in a bit. So I have a naught, which is still a naught, right? I know that it's found to contain 20%. So the new value, the new y value, is 20% of the original, which is just 0.2 times a naught. I'm writing 0.2 times a naught. So a naught e negative 0.123121 times c. The a naught cancels out, and I have 0.2 is equal to e to the power negative 0.123121 times t. If I want to solve for t, I'll introduce natural log both sides. Natural log 0.2 equals natural log e negative 0.123121 t. This cancels out, so I have t is equal to natural log 0.2 divided by negative 0.123121. So t is equal to calculator, natural log 0.2 divided by negative 0.123121. I get 13,301 years. 13,301 years. Okay. This equation is coming from the previous equation, this one here, which is a simplification. Let me show you how it's a simplification, how this, what I have here, simplifies to give me this equation, right? So, on the new screen, I have y equals a naught e to the power natural log 0.5 divided by 5730. I can split this up to be a naught e to the power natural log 0.5 times 1 out of 5730, because this will just go back to that, right? If I have it in that form, then I can kind of split the power, and I say this is e to the power natural log 0.5 to the power of 1 out of 5730, right? Now I know that e to the power natural log is just inverse functions, so what I expect to get is just the 0.5. And 0.5 has a power of 1 out of 5730. Oh, there was a t here missing. There was a t, so there's a t, so there's a t. I was just missing the t. It was there the whole time. Oh man, missing it here too. Yeah, this t, I didn't carry it. So in the equation, there's a t up there. Okay, so this is a naught. The 0.5 is a half, right? And this power here is just t out of 5730. So this is another way, this is the alternative way of looking at this situation, and that is the equation that I have over here, 0.5 or half to the power t out of 5730. So I can use this equation too to figure out how long it takes for this thing to reduce to 20%. So the new value is 20% of a naught, so 0.2 is equal to a naught times 0.5 to the power t, which is what I'm looking for, divided by 5730. A naught cancels out. I have 0.2 equals 0.5 to the power t out of 5730. Introduce natural logarithm. 0.2 natural log equals natural log 0.5 to the power t out of 5730, but that power will drop down. 5730. The power drops down, so I have t out of 5730 natural log 0.5 equals natural log 0.2. So t, if I simplify, will be natural log 0.2 divided by natural log 0.5 times 5730, which if you try on your calculator, natural log 0.2 divided by natural log 0.5 times 5730 gives you the same thing, same answer of 13,301. 4. I'm getting 4 here. So help me double check whether I punched this in wrong. Maybe it was a 4 and I said a 1. I don't remember. But yeah, that's how two different ideas can give you the same answer. Depending on which one is easier for you, you can use that on your homework. This idea of exponential growth and decay is also used very commonly in Newton's law of cooling. And Newton did many experiments. He's a smart guy and came up with this relationship between the temperature of an object at any time t and the temperature of the surroundings and the difference between the initial temperature of the object and its surroundings, right? So this Ts is the temperature of the surrounding air, right? The surrounding air temperature, that is Ts. A is the difference between the initial temperature of the object and the surroundings. K is the constant, which is the continuous rate of cooling of the object. The idea for this Ts is that when something is cooling, it will start off at the temperature of the surroundings, or if the curve for cooling will start off, will have a y-intercept at this point, at the temperature of the surroundings. So how can we use this formula? Let's look at an equation. A cheesecake is taken out of the oven with an initial temperature of 165. So this is telling us that when time is 0, the temperature of this cheesecake is 165. Placed into a 35-degree refrigerator. So since it's placed into the surrounding of the refrigerator, this is going to be the temperature of the surrounding. After 10 minutes, the cheesecake has cooled to 150. They've given us another point that at 10 minutes, the temperature has cooled to 150. If we must wait until the cheesecake has cooled to 70 before we can eat it, how long will we have to wait? So they're asking us for T when the temperature is 70, right? They're asking us for the time when the temperature is 70. Here, they've given us 10 minutes, 150 degrees. They've given us 2 points. This point, that point. They've given us a surrounding temperature, and they want us to find this T. So using this equation, we can first figure out what the equation of this cheesecake should look like. And then after finding its equation, we'll just substitute for y as 70 and get the value of T. So I can start off with this point. When T is 0, the temperature is 165. So I'll have 165 is equal to A, which is what I'll be looking for, the difference, times e to the power k times 0, right, plus the temperature of the surroundings is 35. So if I simplify for this, e to the power 0 is 1 plus 135, sorry, plus 35 equals 165. If I subtract 35 both sides, I'll end up getting A as 130 Fahrenheit, sorry, degrees. 130 degrees Fahrenheit. Okay, so that's my A value. Now I know one thing in my equation, that's 130. I know another thing, that is 35. Okay, and I can use this information here. I can use this information to figure out what K is because I know the T. So using that information, at 150 after 10 minutes it's 150 degrees. So that means 150 will be equal to A, which I know is now 130, times E to the power K that I'm looking for, times 10, because the time is 10 at a temperature of 150, plus 35. Again, 150 minus 35, 115 equals 130 e to the power 10k. So I divide both sides by 130, I have 115 divided by 130 equals e to the power 10k. What do I do next? Introduce natural logarithms. This is a k. Natural logarithm both sides, I have natural log 115 divided by 130 is equal to natural log e 10k. I just have 10k. So k is going to be natural log 115 divided by 130 divided by 10. K, simplify that. If you simplify that, natural log 115 divided by 130 divided by 10, I get negative 0.0122 round up 6. So now my equation, since I've got all of this information, I know what A is, I know what K is, I know what T is. My equation is now any temperature that I'm looking for as a function of T is equal to 130 times e to the power that value, negative 0.01226 times T plus the temperature of the surrounding, which is 35, sorry, 35 plus 35. So using that equation, I can figure out how long I have to wait for it to get to 70. So the temperature is going to be 70, 130 e negative 0.1226 times T, which I need, plus 35. Simplifying this, subtract 35 from 70, that gives me 35 equals 130 e power that whole thing, so negative that T. Divide both sides by 130, so I have divide by 130, divide by 130, 35 divided by 130 is equal to e to the power negative 0.01226 t. What do I do next? Introduce natural logarithms, both sides. Let's create some space. Creating space. Okay, so oh wow, this just got reflected. There's an application of reflection for you. So where was I? I was here. 35. I'm introducing natural log both sides. So I'll have natural log 35 out of 130 equals, on this side I'll be left with negative 0.01226 t. If I solve for t, that's natural log 35 divided by 130 divided by negative 0.01226 t. And if I plug that into a calculator, I have natural log 35, 130 divided by negative, get 1.06, sorry, 106.7 minutes, and that's the same thing as 1 hour and around 47 minutes if you round up. If you subtract 60 from this, it's 1 hour and 47 minutes, around that. Okay, the last idea for today is logistic growth. Now we've talked about exponential growth, but sometimes exponential growth doesn't make sense, because think about this: if Senais gets picked or selected by Disney to be the next Maui in their next movie, Maui Part 2, and he says, "Oh, I have to get a check," so he says, "I'll do 1 push-up on the first day, then I'll double the push-ups that I do every day," right? So on the first day he does 1 push-up. On the second day, he does 2 push-ups. Nice. Third day, he does, what do you think, 8 push-ups, because he's doubling the push-ups he's doing every day. On the 4th day, he has to do 16 push-ups. That's all nice and good. Let's fast forward to the 10th day. How many push-ups does he have to do? He has to do 2 to the power 10 push-ups, right? What's 2 to the power 10? 1024. That's possible. That's possible, 1024. Fast forward to the 20th day. How many push-ups does he have to do? Because he's doubling every day, 2 to the power 20 is a lot of push-ups. 1,485. Wait. Yeah, it's 1,048,000 something push-ups, right? By day 30, he might have to do 1 billion push-ups. And it's practically impossible for Sinai to do 1 billion push-ups in a day, right? Because that means he would have to do around 1,500 push-ups per second just to be able to do 1 billion push-ups per day. So this kind of exponential growth wouldn't be applicable to this model, because as much as this model looks exponential in the first few days, it cannot maintain its exponentiality, if that's even a word. So we need to think of a model that can correctly represent this situation. And that's where logistic models come in. Just like you hear the name, a logistic model, it's logical. It's a logical model. This is the expression for a logistic model. You will, if you study more calculus and stuff, you will figure out how it comes to be this. But for now, we'll just use it and we'll explain the terms. C is called the carrying capacity, or the limiting value, or the carrying capacity, or the limiting value, or the upper bound of that function. So in this situation, if we know that the upper bound of Senai's push-ups is, say, 500 push-ups a day, right? Then that's going to be our limiting value, or our upper bound, or our carrying capacity of this model. This term C out of 1 plus A is the initial value, and it's initial because it happens when x is 0. If you plug in x as 0, e to the power 0 is 1, so your initial value of the function should just be equal to C out of 1 plus A. B is a constant that's determined by the rate of growth. So the rate of growth for Senai's push-ups could be 2, because it's doubling, or it could be 0.5, but yeah, B is just the rate of growth. And this one will just use the model. We'll just be substituting to use the model and try to see how to solve problems with that. An influenza epidemic, so think COVID-19 epidemic, spread through a community of 1,000 people. Now, this 1,000 people immediately tells you that this community, this influenza cannot infect more than 1,000 people in this community, because this community only has 1,000 people. So this is your carrying capacity, or your upper bound, or your limiting value. Logistic growth of B is equal to 0.630, so that's the growth function. Find A if one person is infected with the flu at t is equal to 0. So if at day 0, right, one person has the flu, patient 0, one person has the flu, they've given us a point, t is 0 and y is 1. So the initial value, we can use this to find the value of A, because we know the initial value of the function is equal to C out of 1 plus A, C out of 1 plus A, and this initial value happens when t is 0. So since that's when t is 0, I have 1 is equal to C, which is 1,000, divided by 1 plus A, cross multiply, and I have 1 plus A is equal to 1,000. So A is equal to 1,000 minus 1, which is 999, not to be confused with 666. Okay, so if that is A, then my function simplifies to become C, which is 1,000, divided by 1 plus A, which is 999, e to the power negative bx. Sorry, I also know what b is. So b is negative 0.6030 times x. So that's my equation. And I can use that equation to figure out things like, according to this model, how many people will be infected after 10 days. So 10 days, that means the x value is 10 days. So the number of people, which is going to be the output, will equal C, which is 1000, divided by 1 plus A, which is 999, times E to the power negative 0.6030 times X, which is 10. You plug that into your calculator and get 293.8 something. And since this is people after 10 days, we're going to round it up, right? We're going to round it up because this question is asking for people that are infected after 10 days. At 10 days, if it says at 10 days, then you round it down to 293 because you can't have 0.8 of a person. But since it's saying after 10 days, then we're going to have to round it up because after 10 days, surely the number of people that are infected are more than 293. Okay, yeah, sorry this was a long one, but here's your homework. Enjoy.